All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Wednesday, April the 2nd. Okay, we have a late arrival. We're pushing my grace limit here. Notice from yesterday, the dye, okay? How did it get from, just a drop to the whole thing evenly distributed, even though I've never touched the beaker?
Molecules move slowly over time.
Molecules move slowly?
No.
They're moving actually quite quickly, okay? But they are in continuous motion. And that motion just kind of causes everything to get stirred up as long as the molecules that you're putting in there are tiny, okay? Now, again, that's where we go back to our three types of mixtures. Which one's the smallest particle? First off, what are our three types of mixtures?
Heterogeneous. Yeah, colloid.
Colloid, solution, suspension. Which one's the smallest particle? Probably solution. They're the ones, so this will make a solution, so you're dissolving molecules and atoms, and they're small enough to where the other water molecules hit them, they can all stay agitated. Colloids are medium sized, but when you get to the big particles, like a precipitate that forms, doesn't matter how much the water hits them, it's like a fly hitting a Mack truck, it's not going to move it, it's not going to keep it, and those are the ones that settle out due to gravity, those are the ones you can filter, those are the ones that make it turn cloudy. Okay, but what do we call the process of that natural spreading out of one substance through another? Diffusion. Okay, so today we're going to just kind of finish talking about this, and then we're going to kind of look at some phase diagrams. We're going to take a flashback to the past just for quick review of a heating diagram, okay, and heating curve. But we just need to finish. We have one word blank because you guys are going to freak out if we don't fill in this last blank. Okay?
So right. We have like 6.
No, we already did most of the backside. With 10 is where that's the one.
We didn't do 20. We didn't do 15.
Okay? Well, we talked about it, but you guys didn't fill them in.
No.
That was before spring break. Okay, so number 10. Okay, so what did we call? See, now notice this balloon is still getting smaller and smaller. What do we call the escape of the high-speed escape of the molecules out of this balloon? Effusion. Which one's going to effuse faster, the small ones or the big ones? The small ones. Okay, you're trying to get through a tiny hole. The smaller it is, the faster it's going to be able to get out. So that's why a helium balloon, you have to have that special, mylar, the silvery balloon for a helium, because helium is the smallest of all the elements, as far as atoms, and so it can get through the smallest opening. So if you try to put helium into this type of balloon, it's not going to stay there very long because it can effuse out the openings. Now, here are some terms that we're very familiar with, but we just need to really kind of understand what they really mean. What do we call the escape of high-speed molecules from the surface of a liquid?
Is that evaporation?
Okay, that is evaporation or vaporization. Okay, vaporization. Now, the only difference between vaporization and evaporation is evaporation is from an open container. So the liquid water is evaporating from this beaker. But if we have a closed container, like a water bottle with a lid on it, then it's vaporizing on the inside, and it's kind of forming an equilibrium where it vaporizes and then recondenses, vaporizes, recondenses. Okay? Now, it's the high-speed molecules. So you have another beaker here. The weaker the attractive forces between the molecules, what do you think that does to the rate of escape? Okay? Or to fill us in, the weaker the attractive force between molecules, the blank, the rate of escape. The faster. Okay? So this is the difference between acetone, fingernail polish remover, versus water. Which one's gonna evaporate quicker? Acetone evaporates way quicker. Alcohol, rubbing alcohol, it's gonna evaporate. You know, I was mowing my grass over spring break, but my mower wouldn't start. Because I left the gas in it, okay, over the winter. So I had to dump the gas out into the driveway. Well, it didn't take long for that gas to evaporate. So what does that mean about its attractive forces? They're weak, because it's a non-polar molecule. So what's the only type of attractive force? I know, but what one? Which intermolecular force? London dispersion forces, okay, which are the weakest of all. So volatile liquids, I've defined that before. Anybody remember what volatile liquids means? Okay, are liquids that, so what? Evaporate quickly. So what does that mean about their attractive forces? They're weak. So when we say that something is volatile, that doesn't mean explosive, just means it goes off quickly. So again, when I'm looking here, molecules are all down in here, okay, all over the place. But you have some that are along the surface. They're all being held in by these IMFs. But some are going fast, some are going slow. So when this one hits this one, it might get enough energy, but before it can go anywhere, it hits another one. But when a high-speed molecule hits the one on the surface, bam, it can go. Okay? But it's only going to be the high-speed ones. So if a high-speed one, because you've got to have enough energy to overcome the IMFs, so if the high-speed ones leave, what happens to the average kinetic energy? It goes lower. So when you're wet, and the water's evaporating off your skin, the high-speed molecules are leaving. Well, how do you feel on your skin? Cool. That's why we sweat. Okay, that's nature's way of cooling us off, is that high speed. It takes energy to break that bond. That energy is being converted from the kinetic energy of the water to the potential energy as you break the bond, as the water molecule evaporates. So it's a cooling process. So again, remember, if it's a closed container, that water comes up in here, and now we have the vapor pressure. So if it's evaporating quickly, if it's a volatile liquid, what does that mean about its vapor pressure? It's going to be high, because let's flash back to before spring break. What causes pressure? What causes pressure? It's right there on that sheet. That's how we measure pressure. Say that again. With the container walls. Okay? Collisions of gas particles with the container walls. So if it's evaporating quickly, what does that mean about the number of molecules up here?
There are more.
There are more. So what does that mean about the number of collisions?
There are more.
So what does that mean about the pressure?
More.
It's more. So the higher the vapor pressure, okay? So I think we actually did this when we were doing IMF, but I want you to know this relationship. And just put it somewhere on the notes, on the side, somewhere. But the higher the vapor pressure, means equals weak attractive forces IMFs, okay? And what does that mean about the boiling point? What is boiling? When does boiling occur? Come on now, think back, it's only been a week. Remember I put the water into the, okay? So, boiling occurs when vapor pressure equals atmospheric pressure. So if you have a high vapor pressure, well, actually, let's go ahead and just look at that right now. Okay, how we doing? Does everybody get one? The action one? Does anyone? Yeah. Do we have an extra?
Yeah, that's for sure.
Okay, so this is what we call a phase diagram. All three of our phases can be controlled by temperature and pressure. Okay? So again, if I take just some water out of the tap, normally, I'm going to want to make it boil by putting it onto the fire, heating it up. Because as I heat up a substance, okay, its pressure, its vapor pressure is going to increase. Okay? So when we have 1 atmosphere right here, degrees Celsius. Well, this is not water. Okay? If we have this substance, 1 atmosphere is normal pressure. This is your vapor pressure curve. A lot of times they're going to look a little bit more curvy. Okay? But if I look at the vapor pressure of a liquid, it's going to tend to look like that. And here's 1 atmosphere. So we're going to say for water, this is 100 degrees Celsius. This is temperature. This is pressure. So normally, to make something boil, we have to make the vapor pressure equal the atmospheric pressure. So what do? We put it on the stove, we heat it up, and when it heats up, what does that do to the rate of evaporation? Speeds it up, so we have more vapor molecules. We have a greater vapor pressure. And remember, the atmosphere is pushing down on the surface. The atmosphere is pushing down, and these water molecules in here are trying to form a bubble. So they're trying to push out from one another. But if they push out, what's going to happen to this water level? It's going to go up. So they have to push out with the same force that the atmosphere is pushing down. Well, the way we give them more pressure, the more motion, the more energy to hit the inside of the other molecules, the water inside the bubble, is we heat it up. Eventually, the vapor pressure inside the bubble gets to be equal to the atmospheric pressure the bubble can form. So we normally just heat it up. But if I go and I put it on a vacuum pump, if I put this on the vacuum pump, it's all plugged in. So now I'm sucking the air out of here. Now, instead of increasing the vapor pressure, I'm decreasing the atmospheric pressure, bringing this down to here. Now it can boil at a much lower temperature. And so as the pressure gets less and less and less and less and less, as the pressure gets less and less and less and less, making sure there's no leaks. As the pressure gets less and less and less. Seriously. Well, we didn't seal. Pressure's not wanting to get down very low, I guess. right? That's all cold. There we go. There we go. There we go. So, can y'all, there we go, it's going more vigorously now, you can see it is boiling, right? Okay, so it took a while to get the pressure inside down low enough, but now it's boiling at a much lower temperature. It's boiling at room temperature. I just took it right out of the steam. Okay, so boiling occurs when the vapor pressure equals atmospheric pressure. So as I increase the temperature, I increase the vapor pressure until it's normally atmospheric pressure, but I can also decrease the pressure. So when you go in the mountains, when the atmospheric pressure is less, what happens to the boiling point? It goes down, so your food doesn't cook as quickly. But if I take a pressure cooker and I make the pressure up here, now it's going to boil at a much higher temperature. So the boiling point actually changes every day as the weather changes, ever so slightly, because there's not a huge change in pressure with the weather, but it does change some. We say the normal boiling point is when it's 1 atmosphere. Okay? So we need to know these relationships. That if I have a high vapor pressure, that means I have weak attractive forces. That means I already have more pressure in here, so do I have to heat it up as much? So it's going to boil at a lower temperature. So that means boils at a lower temperature. Now, again, is this water hot? Can I cook my spaghetti noodles in this water? No, they're not going to cook. Even though it's boiling, it's not hot. Okay? So that's again why we have high altitude baking instructions, because the water is a different temperature when it's boiling in the mountains. All right. That's kind of an obnoxious noise. Now we're letting the air back in, and it stops boiling. So this is a heating curve. So as I'm increasing the pressure on the surface of the liquid, what's happening then to the boiling point? So if I'm up here at 2, well, I can't even go that high. Let's go 1.5. It's going to increase the boiling point. So if I'm looking here, where do you think solid, liquid, and gas are? Okay, let me. I'll make it easier to answer that question. Here's A. Here's B. Here's C. Which section do you think is a solid? Look at your temperatures. Okay. A is going to be your solid. Okay? B is where it's going to be a liquid, and C is where it's always going to be a gas. So as I take the pressure off and get down here, there's nothing holding the molecules kind of together. It can be a gas way down even at low temperatures. Okay? What do you think happens right there?
All three plasma.
It can be all 3 at once. Okay? This is called the triple point.
Can you show us that?
I can't really show you that one. You have to have exact temperature and pressure, and it only occurs at 1 temperature and pressure. For water, it's like almost a near vacuum at like 0.01 degrees. But all 3 phases, solid, liquid, and gas, exist at the same time. So what we have here, this line right here, between these 2, okay? If I'm right there, well, let me just kind of go right here. If I'm right there, on this graph. That means that I am at, what do we call the phase change between a solid and a gas? Sublimation, okay? Sublimation, that's the, I think we did that earlier, but you can write this somewhere. Yeah, we did, when we did heating curves, we did it. Sublimation. This is a solid directly to a gas. Okay, solid directly to a gas. That's what dry ice does. That's why they call it dry ice, because it doesn't get wet. It goes straight from the solid to the gas. It sublimes. Okay? So this is at 0.5 atmospheres of pressure at basically 0 degrees. This substance would sublime. It would be going back and forth between a gas and a solid. If it was in a closed container, it would be in equilibrium. It would go back and forth. Okay? As we increase the pressure, that increases here. Triple point, all three exist. So if we go to 1 atmosphere, normal atmospheric pressure, okay, we can count down here, and we can say, okay, well, now this is between a liquid and a gas. What do we call the conversion from a liquid to a gas? We just did it. Vaporization or boiling, right? So this is going to be a measure of the boiling point, the conversion between, the equilibrium between a liquid and a gas right here. So we would always say the normal boiling point is 1 atmosphere, because that's normal pressure. So what temperature is it going to boil? Well, it's going to be, I don't know, is my line straight? It looks like it's probably right at 300, huh? That's to the left. What do we think? Is this line straight?
Absolutely not.
That line is not straight?
Yeah. No, it goes down. No. Like 350. What?
Is that better?
Yeah.
So then if I go straight down from there, somewhere in that range. Okay? So what do we, about 350 would be the boiling point. Okay? Just again, ballpark. So, but we always say the normal boiling point, the normal freezing point is when the pressure is at 1 atmosphere, because that's our normal atmospheric pressure. So we can always, this is going to be the equilibrium, this is when it's going to melt. Now notice, what happens to most substances when it freezes? Does it contract or expand? Contract. Water's an exception, right? Most substances contract. So if I'm increasing the pressure, okay, I'm helping it to solidify, so it can solidify at a higher temperature. I don't have to cool it down as much because I'm pushing it together more, and so it makes it easier. Ice, on the other hand, is different. When you push it together, you're keeping it from freezing. So if it was ice, it's actually going to go that way. And have you ever had the unfortunate experience of having a soda that maybe was in the very back of the fridge, and then when you open it up, it kind of freezes on you? Okay?
Oh yeah.
Because you kind of get an icy, whatever, but sometimes it comes flying out too because it expands. But the pressure, as long as you don't open the bottle or the can, the pressure keeps it from freezing. But as soon as you take the pressure off, now those water molecules can expand and form those open crystal structures, and then it comes, freezes, and makes your icy coming out of, fizzing over the top, and when it freezes like that, it kind of pushes the CO2 out too, and it's not as fizzy anymore. It's kind of flat. But so most substances, it's going to go this way. All right, so let's look at some of the questions. What is the normal freezing point of this substance? The freezing point. Okay, and freezing means it's going from what state to what state? Liquid to solid. Okay, so we're going to talk about that point right there. Right? So you go straight down. Most of y'all said right about what, 100, right? Okay, what's the normal boiling point then? About 350. Okay, it's where it crosses that line. That's where it's going to be an equilibrium between the two states. Okay, Number 3, John, I want to keep the graph up there. What's the normal freeze? Well, the same question. That's just, you know, if I had a quantity of this substance at a pressure of 1.25 atmospheres and a temperature of 300, and lower the pressure to 0.25 atmospheres, what phase transition would occur? So the first one, if I'm at 1.2 atmospheres and 300 degrees, where am I? 1.25 at 300 degrees, I'm right here, right? Somewhere? Approximately?
Yep.
And then we're gonna lower the pressure to what? So basically, I'm coming down to here. So what transition is gonna occur? Evaporation is gonna go liquid to a gas. So y'all can understand how to read this graph? Because we're basically gonna be going down. Right? Okay? Now I'm gonna erase all this stuff off of here just so. Hey, let's take 5 minutes and see if you can answer the questions, even the ones on the back. Okay? So go ahead and pause the video. Oh, there's none on the back of this one? Okay, there's none on, okay. We don't know the answer to this one. Where do you think that point is on question 5? Where would you think the liquid and the gas become undistinguishable? Not the triple point. It's gonna be right here. This is called the critical point. Okay? Now, the critical point, if I keep adding pressure, I'm increasing the boiling point, right? So as I increase the pressure, the boiling point just gets higher and higher and higher. But at some point, no matter how much pressure you put on it, it's got to turn into a gas. So even though they're all pushed real right next to one another, looks like a liquid, they're really separated from one another and acting like a gas. So it's indistinguishable from whether it's a liquid or a gas. In other words, this is the maximum temperature in which a liquid can remain a liquid no matter how much pressure you put on it. Now that's, again, a measure of the attractive forces. The higher the critical point, the weaker the attractive forces. So actually, I said that backwards, sorry. The stronger the attractive forces. Sorry, hopefully I was ahead of you. The higher the critical point, the stronger, because it means it can stay together a liquid longer. Okay? So it's another measure of attractive forces. Okay, so what's number 6 say?
If I had a quantity of recess pressure 0.75 atm and temperature of -100 degrees Celsius.
Okay, stop right there. So we're at -100 and 0.75, so we're basically right there, right? Okay, so then what happens to it?
What phase changes would occur if I increase the temperature by 600 degrees Celsius?
Okay, so 600 degrees, so I went from -100 to 500, so now I'm here.
To 600.
Oh, well, it doesn't matter. Okay, so what phase change is going to occur? All right, well.
Melting and evaporation. It goes through.
It looks to me like it's gonna go a little bit right through, that, so here we're a solid, so then it's gonna melt just for a second, then it's gonna quickly vaporize and become a gas. Right? So we can read this graph. Okay? Do I need to spend any more time talking about this graph? Okay? Solid, liquid, gas. Again, the only thing you need to know differently is that if it were water, this line goes this way for water. So maybe you can draw that in on yours and make sure that you understand. Because water expands, so the pressure keeps it from freezing, so you gotta get it colder. Whereas most substances contract, and so the pressure helps it to freeze, so it can freeze at a higher temperature, not a lower temperature. Okay, there's that. Okay, we did already kind of talk about this, okay? But let's go ahead, if you don't have them filled in, that means that you were just kind of enthralled with the demonstrations and not writing words in. But what do we call the pressure exerted by a vapor above its liquid? The vapor pressure, okay? So liquids that have high vapor pressures have weak attractive forces, okay? Holding the molecules together, while liquids with low vapor pressures have strong, I would say stronger, okay? Because they're really not still going to be strong if it's a liquid. Holding molecules together. Increasing the temperature of a liquid increases the kinetic energy, giving more energy to break the bonds on it together. This causes the vapor pressure to increase. Okay? So we did talk about all this. Boiling occurs when the vapor pressure of the liquid is equal to atmospheric pressure. If high pressure weather system is in place, what happens to the boiling point? It increases, while a low pressure system causes the boiling point to decrease. Right? And this is in the mountains there is less air, and I love the word. It's a great ACT word. The air is rarefied. Okay, means the opposite of compressed. It's real spread out. Okay, which reduces atmospheric pressure. As a result, water boils at a higher or lower temperature in the mountains than at sea level. A lower temperature. So, what are the two ways that we can make water boil? Increase or raise the temperature, or decrease, lower the atmospheric pressure. Okay? Told you we'd talk about it all. All right. 4 main principles of kinetic molecular theory. Okay? I'm just going to say them. You're going to write them. Okay? Number 1. All matter is made up of tiny particles called atoms or molecules. That's key. All matter is made up of tiny particles, atoms or molecules. Number 2. Particles are in continuous, rapid, random motion. The particles are in continuous, rapid, random motion. Continuous, rapid, random motion. And I mean, that just means that, hey, they're just moving. They're just kind of doing their own thing. This is the kinetic theory of a gas. Gases are in continuous, rapid, random motion. Number 3, okay? Collisions between particles are perfectly elastic. Collisions between particles are perfectly elastic. Get that written down, then we'll say what the heck does that mean. Video over here. If I take this ball and I drop it, does it come up as high as from when I dropped it? Why not?
Because it lost energy bouncing on the ground.
It lost some energy when it hit the ground, right? It's losing some energy when it's hitting air molecules, air resistance going down and coming back up. So it's losing energy in the collision with the floor. Well, gas molecules, number one, what is in between in the air? What is in between the oxygen molecule and an oxygen molecule in the air? What's in between the molecules? Nothing. Okay, so molecules don't exert air pressure on each other because it's really empty space in between them. So they don't get that, but when they hit, remember, they don't really collide. Their electron clouds are negative and negative. They just kind of repel, so there's no energy loss. This is an inelastic collision. An elastic collision is one where they bounce off, but they don't lose any energy. So if I take an aerosol can, the pressure inside this aerosol can, even though the molecules are continuously colliding with the container wall, a little bit too close there, colliding with the container wall, they're not losing energy, so the pressure stays the same inside the can. Otherwise, if they were losing friction, every time, the heat would be slowly dissipated out the can, and the pressure would automatically just kind of go down over time. But the collisions are perfectly elastic. They don't lose any energy. Okay, that's what that means. So when all the molecules are bumping against you right now, they're not really hitting you. They're just the negative and negatives are colliding, and they're bouncing off, and they're not losing any energy. All right, that's what an elastic collision means. Is that, you following me on that? Okay, whoops, inelastic, elastic. And then lastly, number 4, basically we can abbreviate it, heat them up, speed them up. Heat them up, and then obviously if you want to write it, cool them down, slow them down. But obviously the opposite's true. If you heat them up, speed them up. Okay? So that's the fundamentals of phase changes. Now we're really going to focus in on gases. But we're going to have to start on that tomorrow. I was supposed to start on that yesterday. But we're just going to take a quick, actually we'll just let you guys use the last 8 minutes and just kind of see what you remember about this. Now, the good news for y'all on this one is that we've already done the math. We're just going to remember the theory part of this. That's 3.
Wait, is this for grade?
I told him I might come to one of those things in Ansley, just for fun.
That's 2 or 3.
But I can't sing. Like, for real. Like, I can dance my
Of the vaporization is this one.
Melted.
Heat of, come on, somebody's got to remember it. So you're closer. It begins with an F.
Super casual. Vision.
You're closer.
Fusion.
Fusion.
God.
Heat of fusion and heat of vaporization. What type of energies are those? Kinetic or potential? Because what doesn't change? The temperature doesn't change. What measures temperature? Kinetic energy. Average kinetic energy. Okay? Now, Sai, you may not have ever had this. So.
What phase of freezing is during segment?
All right, see what you can do with these questions. You guys are just kind of sitting. Look at your temperature. This is water.
Wait.
Boy, it's a solid. It's a solid. It's below 0. It's a solid. What is happening to the energy being absorbed from the heat source? I'm gonna pause this video. Everyone, I hope you have a great day.